So we are starting. Before we start, I'll go through the safeguarding requirements. For the safeguarding requirements, for all tutoring masterclasses and webinars, everybody must follow these guidelines. Microsoft must remain muted at all times. Camera should be turned off. And if you're under 18, please inform your guardian or parent that you are attending the session. And if you have any question, type them in chat. By joining our session, you agree to everything above. I'm Spendylove, a year 13 student who will be helping with these sessions. So today we're going through thermodynamics, AQA specification. So this is the spec. We'll be going through lattice enthalpy, defining lattice enthalpy, and also the types of enthalpies such as the enthalpy of formation, ionization energy, enthalpy of atomization, bond enthalpy, electron affinity, and we will also go through the terms, the above terms and lattice enthalpy, control the Born-Haber cycles, and use it to calculate lattice enthalpies using the enthalpy changes. We will also contrast Born-Haber cycle to calculate one of the other enthalpy changes. Also, we will compare lattice enthalpies from Born-Haber cycles with those calculations based on the perfect ionic model to provide evidence for covalent character in ionic compounds, and also the enthalpy of hydration, and perform calculation on those enthalpy changes. We also go through the Gibbs-free enthalpy change that involves the entropy and the enthalpy itself, and we will describe the feasibility of a reaction and also a temperature at which a reaction is feasible using the delta G is equal to delta H minus T delta S formula. So the learning objectives are: 1, and by the end of the lesson, we can describe the types of enthalpy changes. We can also contract Born-Haber cycles for different compounds. And also we can use the Born-Haber cycles to calculate missing enthalpy values and use values to determine covalent character in ionic compounds. And also using Gibbs-free energy change formula to solve feasibility of a reaction by calculating its respective entropy, and using enthalpy of solution formula to solve the questions. So these are the types of formulas, these are the type of definition we have already seen in energetics. So we already knew enthalpy of formation, one dissociation enthalpy, first and second ionization enthalpy, and also first and second electron affinity. So the enthalpy change of formation is the enthalpy change when the compound is formed from its constituent elements in their standard states under standard conditions. So if you want the enthalpy of formation of ethanol, then we will write its constituent elements in their standard states first. So CS, carbon in solid state, that's its standard state. Hydrogen, H2, is a diatomic, so H2 gas, and oxygen is also a diatomic, so O2 gas, and then we will balance the equation to get the enthalpy of formation of ethanol. And also we were taught the bond dissociation enthalpy, that's the enthalpy change when one mole of a covalent bond are broken under standard conditions in a gaseous state. So chlorine is in its, so this is chlorine. So this covalent bond that's supposed to be joined as Cl to Cl when is broken to form 1 mole of chlorine in its gaseous state. So to balance it, you get 2 more moles of 2 more moles of chlorine to balance the equation. And also the first and the second ionization enthalpy, and the first and second electron affinity. For the first ionization energy, it is the energy required to remove 1 mole of electron. 1 mole of electron from, sorry, I'm letting someone in. Is the energy required to remove 1 mole of electron from an atom to make the atom 1+ ion. That's an ion, a positive ion. And also the second will make it +2 ion. So assuming we want the first ionization energy of sodium, then that's sodium. We are removing an electron, so plus A minus, it must be in its gaseous state. Sorry, I don't have the pen. And removing 1 electron to form a cation, that is Na plus in its gaseous state. And the electrons are balanced on each side. And the electron affinity, instead of removing an electron, it adds an electron to it. And that leaves the compound or the atom to be a negative ion instead of a positive ion. So it's like the opposite of ionization, but not similar. And these are the types of enthalpy in thermodynamics. We have the lattice dissociation enthalpy, which is the energy required to break apart an ionic lattice into its constituent ions in a gaseous state under standard conditions. And this is the example of the formula. So this is the ionic lattice, and we break it apart into its constituent elements. And these are the constituent elements. Its constituent ions, and as in gaseous states. And then you balance the equation. That's the lattice dissociation enthalpy. And this is the lattice enthalpy of formation, which is the exact opposite of the lattice dissociation enthalpy. So the lattice enthalpy of formation, it is the energy required to form an ionic lattice from its constituent ions in gaseous states under standard condition. So it's the exact opposite of the lattice dissociation enthalpy. So instead of going this way, the formula will go the other way. So this will be the formula. You are forming an ionic lattice from its constituent ions in standard states, from its constituent ion in gaseous state under standard conditions. So as written here, they are the opposites of each other. So if the enthalpy change of this was plus 14 kilojoules per mole, Since they are the exact opposite, you multiply this value by -1 to get the value of this. That will be -14 kilojoules per mole. That's not the exact value. I'm just using it for example. And then we also have the enthalpy of of atomization. That's the enthalpy change for the formation of 1 mole of gaseous atom from the elements or compound. Sorry, this is S. This is supposed to be S in its standard state. So it's like the bond dissociation enthalpy, but then it's twice of the bond dissociation enthalpy. So you have to form 1 mole of the gaseous atom from its elements. So this is the element of chlorine in standard states, and you change it to 1 mole of its 1 mole 1 mole of its gaseous atom. And it can also be a compound. That's why it's written as a compound or an element. It can be either of them. So this is sodium chloride in its standard state, and this is 1 mole of each of the atom in the compound in its gaseous state. And since we learned here that bond enthalpy changes 1 mole of the chlorine to 1 mole of the chlorine to 2 moles of it. But for the enthalpy of atomization, it will give you half Cl2 to Cl. So bond enthalpy is twice the amount of the enthalpy of atomization. And we are moving on to the Born-Haber cycle. This is for group 1. So for group 1, when you are starting to draw this cycle, you first draw a long line underneath. That's this line. After drawing this line, after drawing this line, after drawing that line, you first draw one thick line underneath. After drawing that line, you draw another second line. This is the first line you draw. And you draw this second line with the ionic lattice compound. The ionic compound here. The ionic compound will be here. And this will be the atoms in the ionic compound in its standard states. And you try to write the equation here such that it will be the same as here. So you balance this one. So the chlorine in the ionic, since the chlorine in the ionic lattice is 1, you balance it by halving Cl2. And from here to here, as we saw from the start of the lesson, is the enthalpy of formation. So for enthalpy of formation, you are forming the solid ionic lattice from its constituent elements in their standard state. So the arrow points down, and then from the atoms in their standard states to 1 mole of the atoms of chlorine in its gaseous state. So from that to here, we saw that it was the enthalpy of atomization, since chlorine is the only one changing from this state in the standard state to the gaseous state at 1 mole, from balancing it to 1 mole, will be, so this arrow is just the enthalpy of atomization of chlorine. And the same thing is happening here to sodium. It's going from its standard state to 1 mole of sodium in its gaseous state, and that's the atomization of sodium. And the next arrow will be the first ionization energy of sodium. So changing sodium from its gaseous state in atomic state to sodium ions in its gaseous state is the ionization. Since it's going from 0 to +1, it has an electron has been removed from this, like what we So at first, removing an electron from it will give you Na plus. So from Na gas to the Na gas plus is the first ionization of sodium. And from this is supposed to be longer. It's supposed to be almost the same size. This line is supposed to be almost the same size as the line underneath. And then you will write the equation. You draw a line and write the equation for the first electron affinity of chlorine. That's chlorine going from Cl in the gaseous state to Cl minus. So chlorine, this will be the first electron affinity of chlorine. And then from elements in their from the ions of the constituent elements in gaseous state to the ionic lattice was already learned at first. At the beginning, that was the lattice enthalpy of ionization, which is the opposite of the lattice enthalpy of dissociation. So if the arrow was the other way around, though we don't draw it like that, but if the arrow was the other way around, then it would have been the lattice enthalpy of dissociation. So the one given here is the lattice enthalpy of formation. Lattice enthalpy of formation. So to calculate these values, we will follow the root of the arrows, just like in Hess's cycle. So we will try to connect all of them, starting from one place to one place. We can see that from here to here is all going up, and from here to here is coming down. So we can follow this route like this. From here, it can come like this. So the value here, the value from this place to here, from here to here, will be the same as adding the value from here to this place. So assuming we gave you the enthalpy, let me clean it. Let me clean the markers on it. So if we were given the value for the enthalpy, we are given the value for enthalpy of formation. We are given this value and also the value for all of them except the lattice enthalpy of formation of sodium chloride. And to get that, you follow the arrow. Normally, you add all the values from here to here to get this. But since this is what we want, you can do it the other way around. You try to go in the reverse direction. That would be like this. And for it to be like that, the arrows that are pointing down it will be the negative value of the arrow pointing downwards. So you automatically multiply those values by -1 to bring it downwards, and then you get the value of this. So that's what they did here. Negative the value of enthalpy 5, enthalpy 4, then you negate the values since the arrow has changed direction, and then you get the final answer, which is this. But then since enthalpy 1, this didn't change direction, the sign will remain the same, but the rest will change. The sign of the rest will change. You negate the rest because it has changed direction. And moving on. I'm sorry. Moving on. This is also the Born-Haber cycle, but this is for group 2. So for group 2, magnesium is 2 plus, so it will go through the first ionization energy and also through the second ionization energy. So their values will be twice. So the diagram is a little bit different. This is the enthalpy of formation, just like we saw at first, and the enthalpy of atomization of chlorine, since chlorine is the one going from its standard state to gaseous ion in 1 mole. So this is the atomization of chlorine. And from here to there, magnesium is changing from its standard state to, sorry, I'm trying to add other people. And from here to there, magnesium is the one going from its standard state to the gaseous state. So magnesium, this arrow is the atomization enthalpy of magnesium. And then from here to here, magnesium is going from gaseous magnesium atom to gaseous magnesium ion +1, just as we saw at the first, from the second slide, that this is the ionization of magnesium. So this is the first ionization, since it's going from the charge 0 to +1 in gaseous state. That's the first ionization of magnesium. And from this line to that line, is the second ionization energy of magnesium, since it's going from +1 to +2. The sign is changing and it's in gaseous state. You must take care of that. And from here to here, you must balance the electrons for it to be 0, since the enthalpy of formation, from this line to this line and throughout the lines, you can see that all the total charges are 0. So you must balance the charge on each of the lines for it to be 0. So they added an electron for it to be 0, and this too, an electron was added, 2 electrons was added for it to be 0. And from this line to this line, chlorine is going from chlorine gas to chlorine ion, which is an anion. So from the chlorine gas to the chlorine ion, Cl-, as we saw at first, it is the first electron affinity of chlorine. And from here to here is the lattice enthalpy of formation of magnesium. Since this value wasn't given, the enthalpy change 7 wasn't given. For you to get this value, you must follow the arrow direction just like we did at the first time. So from here to here is going in this direction, and it all comes down like this. So from there to there, from here to this will give you the value of this. Since we want enthalpy change 7, you go the other way around. So it will be like this. And since it is the opposite of the normal direction, you will negate the values that are going in the opposite direction. This is going up, so negative enthalpy change 6, negative enthalpy change 5, negative enthalpy change 4, you negate enthalpy change 3, and negate enthalpy change 2. But enthalpy change 1 is in the direction it's supposed to be, so the sign will remain the same. And you can use the values given to get the value of the lattice enthalpy of formation. Moving on, we have to learn how to compare the lattice enthalpies. And we can compare the lattice enthalpies by using the ionic charge. So the higher the ionic charge, the higher the electrostatic charge. So the more positive the lattice enthalpy. So if it is comparing Mg2 plus with Na plus, since magnesium has the higher charge, the higher ionic charge, it will have the higher electrostatic charge. Therefore, it will have a more negative lattice enthalpy. So this the value for the lattice enthalpy of formation for magnesium compared to the lattice enthalpy of formation of sodium, it will be more negative compared to sodium. And also we can compare them using the ionic charge. So the smaller the ion, the stronger the nuclear attraction. Mo- so so the lattice enthalpy will be more negative. And using the same example, Mg2 plus compared with Na plus, Mg2 plus has a smaller ionic radius than Na plus. Therefore, it will have stronger nuclear attraction. With it will be new. It will have stronger attraction to whatever ion it is bonding with compared to sodium. Therefore, it will have a higher lattice enthalpy. Also, the lattice enthalpy of formation is an exothermic reaction, so it will always be negative, and it is the opposite of the lattice enthalpy of dissociation. So the lattice enthalpy of dissociation is positive, since like how we said at the beginning slides. Moving on, we'll go through. Sorry, I'm sending the forms in the groups. So can you please go and check it? I'm sending the feedback form to the group. I've sent the feedback form to the group, so I'm continuing it. So we are looking through the perfect ionic model. For the perfect ionic model, we can use the perfect ionic model to through the theory behind to compare the experimental lattice enthalpy values with the theoretical lattice enthalpy values. So the values for the experimental lattice enthalpy is derived from the balanced chemical equation you are given, or maybe an experiment you do in the lab. And the theoretical lattice enthalpy value is the value given based on the perfect ionic model. Mostly they might say they are given in the data book. So the perfect ionic model, for a model to be perfectly ionic, we assume that the shape of the ion is perfectly spherical, and also there is no covalent character present. And also, some of the since some of the experimental lattice enthalpy has covalent character, some of the experimental lattice enthalpy has covalent character because the positive ion normally distorts the negative ion, which is known as polarization. So if this was Mg2 plus, Mg2 plus, and then, sorry, Mg2 plus, and this is, sorry, and that's O2 minus. At the beginning, let's assume this was a perfect sphere for both of them. After some time, it will change to this size. The size of the negative ion will change a little bit. It will distort like this. So therefore, this is what we see in the experimental lattice enthalpy. So it will have this will introduce as some covalent character in it. Therefore, it will no longer be the perfect ionic model. So the theoretical lattice enthalpy is based on the perfect ionic model. First, this is based on the balanced chemical equation derived from whatever question they give you. And also, sorry, somebody wants to join. So, um, the more it distorts the negative ion, the more the covalent character is present. So the larger, this is it, the larger the polarization effects, the polarizing effects, the more the covalent character present. And if the difference between the experimental and the theoretical values is more than or equal to 50 kilojoules, there is covalent character present. Moving on, we will go through the formula for the enthalpy of solution. Enthalpy of solution is the enthalpy change when 1 mole of ionic solid is dissolved in water to infinite dilution so that the ions no longer interact under standard condition. So this is the formula that explains the description. This is sodium chloride. That's the ionic solid, and it is dissolved in water. So normally some of the equation will add plus AQ here. Plus AQ will dissolve in the water to give you the aqueous ions. So Na2 plus ion and Na plus aqueous ion, and then chloride ion, and then chloride ion. So the chloride ion and the sodium ion will no longer interact, and this happens under standard condition. And the next definition we are looking at is the enthalpy of hydration, which is the enthalpy change. So I think there is a typo. That's change. Which is the enthalpy change when 1 mole of gaseous ion is dissolved in water to form 1 mole of aqueous ion under standard conditions. So you dissolve the gaseous ions. You dissolve the gaseous ions in water to form ionic ions, the ions in their aqueous state. And we have a formula for calculating the enthalpy of solution of the compound. So the formula is the enthalpy of solution of the compound is equal to the enthalpy of hydration of the compound. Normally, it can be written as the sigma, the enthalpy of hydration. So the enthalpy of solution, the enthalpy of solution is equal to the enthalpy of hydration minus the lattice enthalpy, which can be done using the Hess's law. So this is the Hess's law. Which shows that no matter whatever path you take, the total value for the chemical reaction will still be the same. So this is the ionic lattice dissolved in water, giving you the ions in their aqueous state. That's the enthalpy of solution. And from the ions in their gaseous state to the ionic lattice, that's the enthalpy of lattice. That's the enthalpy of lattice formation. And from the gaseous ions to the ions in their aqueous state, that's the hydration of the ions. So you can use this formula to calculate either the enthalpy of solution or the enthalpy of lattice formation, and also the enthalpy of hydration of the individual ions, since you add both of them to get the total value of hydration. So this is the formula. And also we will go through the feasibility and the entropy. So entropy measure is the measure of disorder. So the more disorder a certain system is, the more disordered a certain system is, the higher the entropy. And also if the moles in a reaction, sorry, this is reaction. If a moles in a reaction increases, the entropy also increases. So from gases, liquids, and solids, this is how the entropy, this is the effect of entropy. So for gas, let's say these are gases. Normally, gases are more separated than liquid or solid. And if this is liquid, sorry, if this is liquid, it will be like this. It will be more closer than the it will be more closer than the gases. And also if this is solid, it will be more packed. It will be more packed than the liquid. So the disorderment in the gases is higher than the disorderment of the liquid, which is also higher than the disorderment of the solids. Since there is more disorder in the gases, it will have higher entropy than the disorderment, the higher entropy than the liquid, which also has higher entropy than solid. So normally any element in its liquid state has higher entropy than the same element in its solid state or in its solid state. And if the element is in its gaseous state, it has higher entropy than in its solid state and also in its liquid state. And this is mostly endothermic, which is known as the entropically feasible. And this is the reaction for entropy. That's the S is equal to the entropy of product minus the entropy of reactant. And for this part, if an equation is given and the moles present in the products are greater than the moles present in the reactant, it means the entropy has increased. We are moving on to Gibbs free energy. And this is the formula for Gibbs free energy. This represents the Gibbs free energy. And this is enthalpy. This represents temperature. And this represents entropy change. This is enthalpy change. And this is the entropy change. And this is temperature. Temperature is in Kelvin. And the unit for this one is it can be joules per mole per Kelvin, or you can divide by 1,000 to get kilojoules per mole per Kelvin. And the value for this free energy must be 0 or less than 0. So it must be 0 or negative. It must be 0 or a negative value. And the Gibbs free energy, when the Gibbs free energy is 0 or negative, the reaction is said to be feasible. And rearranging the formula, you can calculate for the temperature at which the reaction is feasible. And this happens mostly when the delta G is 0. And also, you must ensure that the units of the enthalpy change and the entropy change are same before subtracting, because you cannot subtract joules per mole from kilojoules per mole. So if the unit of the entropy change is in joules per mole, you divide by 1,000 to make sure that it will be changed to kilojoules per mole by subtracting. You must take care of that because it can take a lot of mass from it. And also the delta G is measured in kilojoules per mole. And this is the summary of it normally. So this determines the feasibility of a reaction. when the enthalpy change is positive and the entropy change is positive. So let me write the equation. The equation is that delta G is equal to delta H minus T delta S T delta S. So given for a reaction to be feasible, if this is positive and this is also positive, so positive minus positive, because no matter the value of the temperature, multiplied by this will still give you a positive value. So positive minus the positive, it will be negative minus positive, negative plus a positive value will give you positive. So it will be positive plus this. And if the modulus of the T delta S is greater than the value of the enthalpy change, it will give you a total of a negative value. And the negative value, if the negative value is given from this part, we knew that if the delta G is 0 or negative, it means the reaction is feasible. So it will give you a negative value. And also, a reaction can be feasible if the delta H is negative and delta S is positive. Given that so this is the formula. If delta H is negative minus the positive value of delta T delta S, so negative minus positive will give you negative. Negative plus a positive value will give you negative, so it will be negative, and negative plus a negative value will still give you a negative. So the reaction will still be feasible here. And it can also be when the enthalpy change is positive and the entropy change is negative, there will be no effects, and then the delta G will always be positive. Because if we look through here, if enthalpy change, this is positive minus a negative value, and T is here. No matter the value of T, so this will be a negative value multiplying by a negative value, multiplying by a negative value. So it will be positive value adding a positive value, since negative multiplied by a negative value will give you a positive value. So positive value plus a positive value will give you the total of a positive value. So if the delta G is positive, it means the reaction will not be feasible. So it will never be feasible. So there will be no effect. And if the delta H is negative and delta S is negative, it will be unlikely. We can see it here. If to be small. If delta G is equal to enthalpy change minus T multiplied by the entropy change. So if delta H is negative minus T and then delta S is also negative, this will be the negative value, and this time this will give you a positive value. So if this positive value, the modulus of this positive value is higher than the modulus of this negative value. So let's say if this is 50 and this is 60, the total value will be 10. That would be positive 10. So for positive 10, it won't be feasible. So it is unlikely when the delta Ts, the modulus of the delta Ts is greater than this. The value will be positive, therefore it will be unlikely. So it will be usually feasible when this one is greater than that. Yeah, so that's the summary and that's it. Thank you for today. Thank you very much. I'll be sending the feedback form later.